module 2.1, I introduce the definition of probability, then the rules for probability, the notation for rules of probability of A and B, events A and B are occurring, or probability of A intersection B. Similarly, the notation for if given two events A and B, probability of A or B occurring, which is denoted by probability of A plus B or probability of A union B. And then I also introduced the notation for conditional probability. Given that event B has occurred, what's the probability of A occurring? That's denoted as with the probability of A given B or A slash B. Then we went through the product rule, the addition rule, the product rule, the addition rule, and De Morgan's law. We also defined complement. If A denotes an event, what's the probability of A not occurring, which is 1 minus probability of A. In this particular module, module 2.2, I'll work through a set of examples using the probability rules. And we'll start with the first example. What I will do is I will show the slide, describe the example problem, or describe the statement of the problem, and then switch over to solving them by hand. That's what I would do. So we are given in this particular first example that a production lot of size of 100, and it's known to be 5% defective. So that means 5 parts out of 100 are known to be defective. We don't know which 5 parts, and these are parts that are nominally identical. So we pick at random 10 items, and without replacement. We don't replace them. Once we pick 10, there are only 90 parts left. And if event A denotes samples with no defective, what is probability of A? So we pick 10 items. We're asking the question, what's the probability that all 10 that we picked are non-defective? So we want to estimate the probability. So this is an example of what we would call as enumeration, probability estimation by enumeration. Given 100 parts, we know 95 of them are non-defective and 5 are defective. And we want to count the number of ways we can pick 10 parts out of the 95 non-defective parts, so that all samples, the samples that 10 parts that we picked, have no defectives in them. Okay. So, like I said, I'll switch over to OneNote to solve Microsoft OneNote to solve this example problem. So we have we're given that we have 100 parts, 95 of them are good, 5 defective. Sample size is 10 parts, and what we seek is probability that sample is defect free. So that's the probability we seek. So we have now, since we know there are 95 parts, so the probability that we seek is what are the number of ways in which we can pick 10 non-defective parts. And that is picking 10 items out of 95 items. We know that the population has 95 non-defective parts, and this is the number of ways in which we can pick 10 10 non-defective parts. Now, the number of ways we can pick any 10 parts is if I just pick 10 parts, regardless of whether I'm picking defective or non-defective, the number of ways in which I can pick 10 parts is combinations of 10 items out of 100. Previously, I had combinations of 10 items out of 95. So you can think of this as the total number of ways we can pick 10 parts. And previously, we had the number of ways we can pick 10 non-defective parts. So therefore, the probability of event A, which is, so this is defined as event A for us. So probability of event A is the number of ways in which you can pick 10 non-defective parts divided by total number of ways in which we can pick 10 parts by using the definition of probability, the first definition of probability that we had. So this is pure enumeration. We are counting the number of ways event A can occur divided by the total number of ways in which an event can occur. So this would correspond to cap n in our definition, and this will correspond to little n in our definition. And we are using the first definition of probability in order to carry out this enumeration. This is example 1, so I should put example 1 here. Okay, so next I'm going to work out example 2. So in example 2, we have 2 unbiased dies and they're rolled. What is the probability that the sum of the 2 dies is 9? These are unbiased, meaning that they have equal probability of getting any of the 6 faces to roll up. So any one side has probability of 1/6, occurrence of 1/6. And we want the sum of the 2 dice to be, the numbers on the 2 dice to sum to 9. So in example 2, what we seek is probability that sum is equal to 9. So for in any roll of die, we have 6 possible, any number we have, probability of any number is 1/6, or any there are 6 possible numbers. So the total number of total combinations that we have, total outcomes that are possible is 6 times 6, which is equal to 36. So those are all the total number of outcomes that are possible. We have to enumerate the subset of these that can sum to 9. Subset of these 36 events leads to sum of 9. And the possibilities are, so this is either you have 3 and 6, 4 and 5, 5 and 4, or 6 and 3, where these numbers correspond to the first die and second die. So this is equal to 4 events, 4 possibilities. 4 of these 36 events yields a number equal to 9. Therefore, probability that the sum would equal to 9, which let's call that event A, that's equal to 4/36, which is 1/9. So that's the number that we seek. Again, by enumeration. So this is little n, this is cap n. So by enumeration, that is the probability that the sum of two dice would be equal to 9. Okay, so let's move on to example number 3. So 8 kings and queens are removed from a deck of cards. 4 kings and 4 queens are removed from the deck of cards. And then 2 of the 8 cards are selected. What's the probability that the king or queen of spades is among the cards selected? So we pick 8 cards from a deck, and only the kings and queens are picked from the deck, and I pick 2 cards out of the 8, and I ask the question, what's the probability that king or queen of spades is among the cards selected? So we have 8 cards and we pick 2, and the question is probability that king or queen of spades. So the key word here is R, queen of spades is in the selected. So here the key is that it's king or queen. Okay, so we need to define events here. So in any probability problem, it's important to define events. So let A be the event that one of the cards, one of the 2 is king of spades, and B be the event that one of the 2 is queen of spades. Then what is the probability of A? Probability of A is given by, we don't know how to calculate this yet, but let's say how many ways can I pick 2 cards out of the number of ways I can pick 2 out of 8 is 2 items out of combinations of 2 items out of 8. Let's say one card I've already picked, and that is the king of spades. So then I have 7 ways I can pick the second card, right? So essentially the probability of A would be, the little n would be 7 ways I can pick the second card, because the first card is already picked. It has to be king of spades. I don't have a choice there. However, once I pick the king of spades, there are 7 ways I can pick the remaining card, the second card. And the number of ways I can pick, the total number of ways I can pick 2 cards, independent of any restriction, is 2 items out of 8, combination of 2 items out of 8. Okay, 8, that's basically 28. So that's 7 over 8 times 7 divided by 2 times 1. Okay, n factorial divided by n minus r factorial times r factorial. And so that is equal to 7 over 28. That's 0.25. So this number 7 is key. So this is little n. This is cap n. The denominator tells me how I can pick 2 cards out of 8 without any restrictions. The numerator tells me the number of ways I can pick king of spades. Once I picked king of spades, there are 7 possibilities for the second card. Similarly, probability of B is exactly the same, because once I picked queen of spades, there are 7 ways I can pick the second card, and the total number of ways in which I can pick 2 cards is combination of 2 items out of 8. This is again 0.25. The question that I seek mathematically is probability of A union B. This is what I seek. Probability of A union B is probability by the addition rule. It's probability of A plus probability of B minus probability of A intersection B. Now, what is the probability of A intersection B? The probability of A intersection B, the number of ways in which I can pick both king and queen of spade, is there's only one way. I don't have any choice at all. There's only one way I can pick them out of a total of 28 ways I can pick 2 cards. There's only one possibility for me to pick both king and queen of spades. So that's 1 over 28. So therefore, probability of A or B, king or queen of spades being picked is 0.25 plus 0.25 minus 1 over 28, which turns out to be 13 over 28. That's the probability of picking king or queen of spades from a deck containing all kings and from 8 cards containing kings and queens. Okay, so last example. So here's a baseball example. The batting average of a baseball player, the number of hits divided by at-bats is 0.300. Baseball batting averages are written with to 3 decimal places, 0.300. And that's considered an excellent batting average. So in 2 at-bats, what's the probability that the player will hit at least once? What's the probability that in 3 at-bats, the player will not hit at all? And what's the probability that the player will hit at least once in 3 bats and 3 at-bats? So that's the question. Let's go through and solve this problem. So first, as with any probability problem, first we have to define events. So we need to define, this is a critical thing to do in any probability problem, define events. A1, and again, when you define events, you want to define the simplest possible event and define more complicated events using combinations of these simple events, such as let's define event as hit in first at bat, and define A2 as hit in second at bat, and A3 as hit in third at bat. So this is a simple event. Now what we seek in question A is the probability that in 2 at-bats, what is the probability of hitting at least once? Now in order to compute this, we need to know probability of each of these events. Probability of A1, on an average, the player is able to hit with a probability of 0.300. Now each of these at-bats is an independent event. So the first time whether the player hit or not has no bearing on the second time whether the player would hit or not. We will treat them as independent events, and therefore probability that the player would hit in the second at bat is 0.300, as is the probability that the player would hit in the third at bat, that's also 0.300. So the question that we seek is, in 2 at bats, what is the probability of hitting at least once? So first, again, in all of these probability problems, the first thing we want to do is to define events and define simple events, and then turn the wording, the statement, into an equivalent mathematical statement. So what we seek here is probability that you would hit in event A1 or event A2 occurring. That's the question that we seek an answer to. So we are seeking what is the probability of event A1 or A2. So that's the equivalent mathematical statement. So in 2 at-bats, what's the probability of hitting at least once? And so this we know from our addition rule is probability of A1 plus probability of A2 minus probability of A1 and A2. And we know A1 and A2 are independent events. So therefore, this quantity is nothing but probability of A1 times probability of A2. So this is going to be equal to 0.3 plus 0.3 minus 0.3 times 0.3, which is equal to 0.24. So in question 2, what we seek is what's the probability that no hit in 3 at-bats. So the way to mathematically state this is no hit in the first at-bat, which is A1 complement. A1 would the probability that he would hit in the first at-bat. A1 complement is the probability that the player would not hit in the first. And so therefore, since the way we are defining events is through and, so therefore we need to put intersection, probability that the player would not hit in the second at-bat, and the probability that the player would not hit in the third at-bat. So that's, and if A1, A2, A3 are independent events, so are A1 complement, A2 complement, and A3 complement. Not hitting are also independent events. Therefore, we can write them as probability of A1 complement times probability of A2 complement times probability of A3 complement. And each of these is 1 minus probability of A1 and so on. So we can write this as 0.7 times 0.7 times 0.7. That's equal to 0.343. That's the probability that the player would not hit in 3 at-bats. And the last part is probability player at least 1 hit in 3 at-bats. So what we seek here is probability that the player would hit in either the first at-bat or therefore union, or the second at-bat or the third at-bat. And that's really what we seek. And we know this. You can apply, you can do this using either the summation addition formula, or simply this is by using De Morgan's rule. This is nothing but 1 minus the probability that the player will not hit in the first at-bat, will not hit in the second at-bat, and not in the third at-bat. And that turns out to be 1 minus 0.343, which we estimated in part B, and that's 0.657. Now, if you want to check the more elaborate formula, addition formula, if you want to check using the more elaborate formula, we can do that as well. Union A3 is probability of A1 plus probability of A2 plus probability of A3 minus probability of A1 intersection A2 minus probability of A2 intersection A3 minus probability of A3 intersection A1 plus probability of A1 intersection A2 intersection A3. And substituting values, this is 0.3 plus 0.3 plus 0.3. So let me just write this as minus 0.09 minus 0.09 minus 0.09 plus 0.3 cubed, and this again turns out to be 0.657. Okay, so those examples illustrate how to use the probability rules. And with this, I'm going to stop this discussion of module 2.2 on probability rules examples. Next, we will introduce conditional probability. Thank you.